Hello everyone, how you doing? Good to see you all. Welcome back on this Thursday evening, and we're going to just carry on where we left off yesterday. We were looking at a March paper and the paper one, and we're just going to carry on where we left off. So let me swap to looking at the screen. And yeah, we got to this question. So it's the March 2023 paper. Remember, the March papers are specifically for India. They have that so many people take the exam in India, they have their own sitting. But it's great because it gives us an extra paper to do the work with. And yeah, so we were on question 2, so fairly early on. And we've done question A. We're now on question B. If a programmer, so we actually just very quickly recap. So in this question, we ticked one box to identify if they should use high level or low level. And we saw that basically it didn't matter which you picked, you just had to justify. And it was just about why you would choose one language over the other. So a programmer chooses a high level language, and they can use a compiler or an interpreter to translate the high level language into a low level language. So describe the operation of a compiler and an interpreter. And there's 4 marks. So basically 2 points for the compiler and the interpreter. Okay, so for this, we're just kind of thinking what is the crux of what a compiler or an interpreter does. And I've just realised I haven't opened up my Zoom whiteboard. I knew there was something I hadn't done. Hold on, just give me 1 second to open that up. Just give me 1 sec to open this up. Okay, so there we go. Okay, there we go. Sorry about that. Yeah, so let's think about what a compiler and an interpreter does. So a compiler is, it's different languages, but ultimately what the compiler does is it produces an executable file, or exe file. It also is done by the software developer or the programmer. So when I say it's done by the software developer, I mean turning the code into binary, basically, or machine code. So it's done at the time of development. That's sort of the main 2 things. Another thing you could say as well for the compiler is that that's all you need. So the executable file is all you need for distribution. So you don't need to give them anything else. Because we're turning it into binary at the time by the programmer, we don't need to give the translator to the user. So the difference is with an interpreter, so languages like Python, for example, you don't get an executable file. It runs, or it turns it into binary at the time you run it, or as you run it. Sorry about my appalling handwriting. So you don't get that executable file. So that means the user must install the interpreter onto their machine. And now that's good or bad. I mean, Java is an interpreted language, and lots of people just install the Java runtime environment and they can then run anything. And you can, I think there is an equivalent. I'm pretty sure. I haven't distributed any of my code in Python. I've only ever done small projects for teaching, but I believe there is a mechanism that you can use to get your work, your Python code to run, and you can sort of give people Python at the same time as your code. So that's kind of like the crux of it. Remember, with an interpreted code, it turns the binary as you run it. So it is literally line by line. Let's have a look at the mark scheme, because I'm sure I've left something off there. Let's have a look. It's question 2B. Yeah, so here we are. The compiler checks all code before executing any code. It produces an error report for all of the errors in the code, and it produces an executable file. There is other stuff to that though, so that is really brief. Checks and translates. So the interpreter, like Python, checks and translates one line of code and then executes it before moving on to the next line. It stops when an error is found, and when it's corrected, the program can then run again. So that's what happens if you've ever run your Python. Sort of, you know, you think everything's fine, and then it just bombs out, and you're like, I've got a massive red error. What's going on? So yeah. So that's it for those two. If we just have a quick look at the question again. Yeah, so it says describe the operation of it. So I probably went into a bit too much about distribution, but that's fair enough. Okay, next question. A new computer comes with primary and secondary storage. Data storage is measured using binary denominations. Complete each conversion. So we're using the IEEE method here. So that is with megabytes, petabytes, etc. So see if you can work out any of these before we start looking at the answer. Can't be a maths question on a Thursday night. And don't worry too much if you're kind of like, oh my goodness, I don't know what I'm doing with this. It's absolutely fine. I mean, I think I said last time that this exam paper is for India basically, and some of the language can be quite simple, but it doesn't mean it's easy. they like, yeah, we're going to set you some really hard questions, even though the way that we describe it's really easy. It's like, it's a bit mean. All right, so basically for this, we need to think about the sort of the hierarchy of the different values. So obviously we've got bytes and nibbles, anything up to sort of, 8 bits are in a byte. That's fine. So if we've got 8 bytes, how many nibbles is that? Well, it's double that, it's 16. So remember that a byte is 8 bits. I'm just going to put random bits. So we've got 8 bits in a byte, and if we've got 8 of those, then that is 8 bytes. 8 bytes. 8 by 8. But a nibble is half a byte. So ultimately, you're just doubling it up because each one of those is a nibble. That's a nibble. So there's 16 because it's 2 for every 1 byte, which is 16. So the answer to that first one is, it is 16 nibbles. Okay, so let's look at the larger quantities though. So we've got megabytes, or actually we haven't got megabytes, we've got kilobytes first. So we've got kilobytes, and kilobytes are basically 1024 bytes. Then we've got megabytes, and that is basically 1024 kilobytes. So it does go up in the same way as the old system. So I call it the old system, kilobytes, megabytes. Instead of going up by 1,000, it goes up by 1024. Then we've got gigabytes, and gigabytes is just 1024 megabytes. And then we've got terabytes, which is 1024 gigabytes. And then we've got, are they going up to exabytes? Yeah, so we've got petabytes. Don't know why they're going this high. Is 1024 terabytes. And then the last one, they've got exbibytes. Such a mouthful. Exbibytes is 1,024 pebibytes. So now that we know that basically we've got those tiers, you know, is the equivalent would be kilobytes, megabytes, gigabytes, etc. But we're just rounding it to 1,000, or it's 1,024. It's more specific. We can work out what to do for the other one. So the next one is 512 kibibytes. How many mebibytes is that? Well, if we look at where kibibytes and mebibytes are, it's times 1,024. So if we've got 512, that's half. So 1,024 divided by 2 is 512. So that basically means that in mebibytes, 512 kibibytes is half a mebibyte. So 0.5. So the second answer is 0.5 mebibytes. So 512 kibi is 0.5 mebi, because it's half of that step up, if you see what I mean. The next question is 4 gigabytes. So how many mebibytes are in 4 gigabytes? Does anyone want to try that one? So we're basically going between gigabytes and mebibytes, these two here. What's the difference between those two? Well, it's 1,024, remember, because it goes up. And we've got 4 gigabytes. How many mebibytes is that? So we've got 4 of those. So someone else is, so I'm just looking at the chat. 1,024, it's 1,024, yeah. A bit is a byte divided by 8. Yes, that's right, yeah, good. Yeah, so basically, if we've got 4 mebibytes, we've got 4 gigabytes, 4 of these, how many mebibytes? Well, each one is 1,024, so it's just 4 times 1,024, because we're going up that step 4 times. So that is basically 2048 is 2 of them. So 2048 plus 2048, that is 6, 8, 16, 4, 8, 9, 0, 4. So 4096. So the second one is, there's in 4 gigabytes is the same as 4 GB equals 4096 MIBI. Okay, so the next one is, or the last one is 1 exbibyte is how many pebibytes? So again, we're just going up by 1,024. So if we've only got 1 exbibyte, how many pebibytes is that? It's just 1. So basically it is 1 exabyte equals 1,024 pebi. I don't know why it said pebi, but it's got an I. It's just very odd. And that's not Tibby, it's Tebby. Sorry. So I think with this is just to remember the 1,024 going up. They don't tend to ask anything outside that. And yeah, it is not the easiest thing ever. Let's have a look at the mark scheme, just to check I've got that right. So I've got 16. Yeah, that'd be good if I got it wrong. Yeah, no, that's all correct. Good. Excellent. It's always good when the teacher gets it right. Okay. So let's move on then. And the next question is about RAM. Random access memory is an example of primary storage. Give 3 examples of data that is commonly stored in RAM. So 3 examples of data that's commonly stored in RAM. I find it really interesting how the YouTube thing says there's 8 people, then there's suddenly 4 people, then there's suddenly 8 people. It's like, make your mind up, YouTube. So let's think about what RAM is. So remember that what RAM is it's part of the main sort of mechanism of a computer. We've got a CPU, which is our main chip. We've got RAM, which physically will sit very close to the CPU because they talk a lot. And the RAM sends data and instructions to the CPU. We've got our secondary storage as well. And the thing with RAM is, obviously, it's volatile. So if we switch off the electricity, everything in the RAM is lost. That's good though, because it means that if you've got problems, you switch the computer off and on again, it will clear out the RAM. And that's why that works. So what is it storing? It's storing all the programs that we're currently running, because if you start your computer up and nothing's running, you sort of click on Minecraft or you click on Word or Zoom or whatever, it gets all that from the secondary storage and loads it into the RAM. So it will always have programs running, or programs currently running, I would say. It will also store data that is being used by those programs. And do they want 3 things? Okay. Now what's the third thing? Let's have a think. So one of the things that they will also have is parts of the operating system. So you can kind of keep that separate. So the operating system will also be in there as well. Let's look at the mark scheme, see what I've left off. So yeah, currently running data, currently running applications, currently running instructions. So they're just kind of going into a bit more detail of the programs that are running, currently running parts of the operating system or utility software. So very similar to the operating system, that anyway. Okay, next question then, if I can find it. Describe the purpose of secondary storage. I've just described that already when I was describing RAM and everything. So it doesn't matter. Let's look at the answer. So it's non-volatile permanent storage to store data that's not currently required by the CPU, to store data to transfer it to another computer. Don't know whether I'd have picked that one out, that last one, but yeah, it's permanent storage. So if we switch the electricity off, it's always there, and it's not currently required by the CPU. Okay, next question then. A wildlife photographer stores their digital images on a computer. Complete the table by defining each term about images, pixel and resolution. They do keep asking this actually. This has appeared quite a few times since 2023, not only just for images but also for sound. So it's a good one to kind of look at if you're thinking, you know, does it come up often? And it's like, yeah, it does actually come up quite often, this one. Someone's asked, but actually before we do that other one, someone's asked, why don't computers use the CPU to store data that is currently being used? So they do actually store some of that. that's called static RAM. So there's actually dynamic RAM. This here, so just to digress on that one, this is dynamic RAM that we have. The CPU does have its own RAM. We normally don't call it RAM though, we normally just call it cache. And it's used a lot. And actually one of the ways that you might have heard of the Apple chips, so the Apple M1 or M2, I think they're up to M4 now, M4 chips, etc. They are super fast. They're a really big advance in computer chips, actually. And the reason for that was they had a massive increase in cache on the CPU. So they're faster. They don't keep having to transfer stuff to the dynamic RAM. The cache was much bigger. Obviously, it's more expensive, but there's only a certain amount that you can sort of get on the CPU without it being too physically big as well. So they are constrained by physical size, not just, they probably would add more if they could, I think. But otherwise, the CPUs are just going to get so large, they're going to be as big as the RAM. So it's a kind of a trade-off, as making sure that you get as much as you can, or as much cache as you can on the CPU without it, transferring too much to the RAM. And yeah, because it could just end up where you just have a CPU and the RAM joined together, and that it's just going to be huge physically. But yeah, that's one of the reasons why Apple got them, a lot faster. Another problem is though with that cache is it's really expensive. So this is known as static RAM, and it's actually really, really expensive. So cost is another reason. And yeah, you can sort of talk about how Apple are more expensive, and one of the reasons is, especially with the M chip series, is because static cache is more expensive. Thank you. Thank you very much for that compliment. Good. I aim to please. I'm just trying to get you all to be fantastic programmers and computer scientists. So, a wildlife photographer stores their digital image on the computer. Can we define a pixel and the resolution? I think pixels as well. Pixels is one of those things where you you kind of know what it is, but actually defining what it is in an exam is quite hard. It's like you could say, it's a dot on a screen, but that's not quite. It's not computer sciencey enough. So yeah. So a pixel is basically the smallest component of an image. So that's probably the best sort of definition, the smallest component of an image, and the resolution is basically the number of pixels in an image. So let's look at the mark scheme. So they've got a pixel is one square circle of colour, or you could say, so the double slash means or, you could say the smallest component of an image. I always just go for the smallest component of an image. And then the number of pixels per set area, or I usually just go for the number of pixels in an image for the resolution. But you can do kind of like the width versus the height and all that type of thing as well. So actually, they're quite nice, easy definitions, really. We've got another maths question. One of the images has a resolution of 1000 times 1000 and a colour depth of 2 bytes, so 16 bits effectively. Calculate the file size of the image. Give your answer in bytes. So this one's in bytes, not megabytes or anything like that. So it should make the calculation a little bit simpler. So let me just get my whiteboard here. Does anyone? I'll just give you a moment in case you want to try this. Actually, see if you want to try it first, and then yeah. See if you can work this one out. You didn't know pixels are circles. Yeah, I think they can be, but Okay, let's think about how we're going to work this out. So basically, it's a fairly easy calculation actually. Even for me, and my maths is really bad. We've got 1,000 by 1,000 colour depth, so 1,000 resolution. So the first thing to do is always find out how many pixels you've got. So we've got 1,000 times 1,000, and 1,000 times 1,000. You just add together the zeros, and that gives you, or you add the zeros on. So that basically gives you 1,000,000. So we've got 1,000,000 pixels in that image, and then it's a colour depth of 2 bytes, and they want you to give it in 2 bytes. So we don't even have to worry how many bits. So it's just basically 1,000,000 times 2, because it's 2 bytes. So it's actually 2,000,000 bytes is the answer to that one. So nice and easy, even for me, my terrible maths. So let's look. Oh, I hope I got it right. Yep, 2,000 bytes. So you get 1 mark for that, and then 1 mark for your working. And even if you didn't get both the workings right, you can still get a mark for just one of those. So that's good. Okay, let's look at the next question. We are steaming through this one. We have got another question on, we're filling in the gaps. These are always good. A photographer decides to purchase a solid state device to back up their images. Complete the description of solid state storage. Use the terms from the list. Some of the items in the list will not be used. You should only use a term once. Okay, give this a go. Go on. You can do this. I'm sure you can. I'm just having problems connecting to the YouTube, so I can't see any comments at the moment. So I'm just going to try and reconnect it. Probably my son has gone on the internet. That's probably what it is. Yeah, it doesn't want to do it. Anyway, I'm going to go through it. I can't see what anyone's put in the chat at the moment. So, which is a bit annoying. Anyway, so the first one, solid state storage. I'll put these on separately here. Solid state storage is non-volatile. That's the first one. So that means that the data is not lost when the power is turned off. Solid state storage is made of transistors that are laid out in a grid. Gates are used to control the flow of electrons through transistors. This changes the data in the transistors from 1 to 0 or 0 to 1. So it's non-volatile, transistors, grid, and electrons. Okay, let's move on. The photographer compresses an image file before it is emailed. Give one reason why a file is compressed. Why do we use compression? Oh, I should have just checked my answers for that one. Non-volatile. Yep, good. There we go. Why do we compress files? So nice and easy. It's basically to make it smaller in storage size. So we compress to make the file smaller. So to reduce the file size, to increase transmission speed as well, reduce the storage space required, or less bandwidth required for transmission. So any one of those, but yeah, really it's just to make it smaller, isn't it, really? Okay, next question is, a website allows users to purchase items. A computer A sends a request for a homepage to the website's user server. The structure of the packet data has 3 elements. One element is the packet header. Identify 2 items of data contained in the packet header. They do like asking about this because this one is a new for the 2023 syllabus. So although it's going to be 2026, they still like asking about it. Yeah, good. I can just see your answers now for the previous question. So well done, everybody who's done those. Good. Excellent. I don't know why my iPad is not showing. So 2 items of data in the packet header. IP of the sender, the amount of data contained. Yeah, good. Those 2 are good. Excellent. So yeah, if we look at the packets, let's look at packets. We've got, there's our data packet that we're sending over the internet. We've got 3 sections. We've got the header in this section. We've got the payload or the data in that section. And then we've got the trailer. And in the header, there's more stuff going on in the header. Obviously, the payload is the actual data you're sending, so that could be anything. The trailer only has the checksum, which is an error checking mechanism, which I'm sure will come up later in this paper. They always do, or something along those lines will. And then we also have in the header a number of things. We have IP address of the sender, IP address of the receiver, and we also have, not very good spelling today, you can also have the packet number, which of, you know, if you've got 1,000 packets for what you're sending, this could be packet 18 of 1,000. Yeah, and the amount of data that you're sending, yeah, that I think that's in there as well. Now, if we look at the mark scheme, let's see if I've left anything off. I don't think so, but have I forgotten anything else? Yeah, destination IP address, packet number, originator IP address, error detection. So they've got error detection method. So yeah, so whoever said checksum, you would get that as well. So that's basically saying which error detection method they're using, I think, rather than the actual one. But this has got EG. So if you did say something else and it's on the header, and I think the size of the data is on that, then that should be fine as well. Okay, next then, identify 2 other elements of the packet. I've just told you what they are. So obviously it's the payload and the trailer are the other 2 elements. So yeah, they do like these to ask you about data packets. A Okay, next question. Computer A needs to be directly connected to a router that is located in a different room. Tick one box to identify whether serial data transmission or parallel data transmission is more suitable for this connection. So it doesn't say how far. So I'm guessing, yeah, you can pick either serial or parallel. You just got to justify it. It doesn't matter because they don't tell you how far the room is. So the room could be just literally a metre away. So serial or parallel, give reasons for your choice. Obviously, you don't get any mark for picking serial or parallel. It's just 3 marks for the choice. So if we think about the difference between serial and parallel and what they're really getting on about with this, we are covering such a lot of the syllabus today actually. But if we think about serial, what serial does is we got one wire. So that's the key thing, one wire. And we're sending the data 1 bit at a time. And there's a very slight delay in that, 1 bit at a time. So if we're sending our data, we'd have, you know, the data going down like that, but there is a time delay between each bit being sent. Now, obviously that time delay differs between different methods sending the data, but obviously it is very, very small amounts of time. What else about serial? We use it over long distance. So basically anything over 5 metres. So probably the room is going to be more than 5 metres, but you can put that in your answer, say it's probably going to be more than 5 metres, so we're going to need serial. And it is still fast though, so serial is slower than parallel, but it's still fast enough because we use serial for most places anyway, so you know it is sufficient effectively. And then with parallel, we've got many wires and we're sending data bytes at a time, or minimum bytes at a time. So we're sending, you know, this byte, I know it's only 6 wires, but you get the idea. There's still a time delay between sending it, but we're sending a byte at a time or more instead of just one drip by drip. So this is definitely, it is faster. So you could say in your answer it's faster. It's probably not going to be too far. So if it's in the next room, it's, you know, not too far. Now the problem actually I didn't mention in the previous one with serial is you don't get any, or there's less interference. So part of the problem with parallel is these wires, because they're electrical cables, they will they will interfere with each other and the signal. So that means you might get bits disappear because of the wires interfering, and so you could get more errors. So there is more errors with parallel, but because it's in the next room, it should be okay. So it should be okay if it's not too far. You know, as long as you're not in a massive airport style massive room. So yeah, so that's basically the difference. And they do like to ask questions about this. It's a very common question. And what have they put that I've forgotten? So we've got, so if you said serial, they've got the data arrives in order that it's been sent. So that's something I didn't mention actually. Yeah, the data arrives in the order it's been sent. And actually the parallel can get out of sync. So that's something that, you know, you might get it slightly skewed in that sense. And it's less likely to have errors with serial. You can transmit over longer distances, still fast transmission, sufficient for this purpose. So you can sort of justify it. Parallel is faster than serial. It has faster response to requests. It's not a very long connection is needed. And the next room is likely to be sufficiently near for parallel and therefore unlikely to arrive out of sequence or skew. So yeah, just go with which one ever you can remember the most of though. You might think, that's not the best one, but they do let you pick either, and just pick the one that you can remember the most to answer and get those 3 marks. So the connection will also use full duplex data transmission. Define full duplex data transmission, and you should be able to do it in like one sentence actually. So let's look at the duplex, etc. Now this is different to serial and parallel, and quite often my students get mixed up between the two. You know, duplex, serial, what's going on, what's the two? Remember that the serial and parallel is the physical wires that you use to transfer data. So the physical wires is serial and parallel. And the duplex side of it is the direction of travel. So the direction is direction of travel of the data. That is simplex is the first one, and that is one direction only. And so that would be things like a keyboard or a mouse or the graphics tablet that I'm using to write this. And it is usually sort of input devices. Then we've got half duplex, and half duplex is both directions but not at the same time. So like a walkie-talkie is a good example. Does anybody use those anymore? I have seen them, a few people. I've seen them in some shops, and I've seen people like at car boot sales, and they're like a family or a couple, and the husband and the wife have one each, and they're talking to each other like, oh, I found something in the car boot that might want to have a look at. And that's quite funny seeing that. And then what we're on here, what they're asking about is full duplex. So this is the last one. So full duplex, or you can just say duplex. I think they've said full duplex to clarify that it's not half duplex, but this is both directions at the same time. And this would be a network, for example. So network cable or Wi-Fi, something like that. Wi-Fi network. So yeah, it's different to the serial parallel. Don't get them mixed up. It is easy to, but obviously you can mix them together. You can have serial simplex. You can have, parallel full duplex, but they are different things. One's describing the physical way, and then the other one is describing the direction of travel. So we've pretty much run out of time. Have we got time to do the parity question? We'll just, no, we'll leave it because when we come back in January, we'll do the parity question, because if we don't, then then it carries on with a parity block question. So we'll leave it there. Hope that's been helpful. Thank you everybody for coming, and keep revising. And I'll see you in January. So these will continue on a Wednesday and Thursday night, but starting on the week of, not the 8th, it will be not the 1st of January, because that's New Year's Day. It'll be the week after. So that is, what's the date of that? So that's the 8th, the 7th. The 7th and the 8th of January is when we're back. All right, take care everybody, and see you again.